Thanks for coming. I'm Reka. I'm a graduate student from Hungary. My topic is static analysis on the source code level, which is kind of far away from what I like to show you today. So please be gentle with your questions. But I found these two tools that I'm going to show you, and I had no idea how they work, but they were fascinating. So I decided to find out, and I'm here to share with you what I found. One more thing, I owe you an apology. So the talk went through an evolution process during the last few weeks, and the title might not be like as good as it was. So a more honest version would be like two binary analysis tools, only one of them is strictly connected to compilers, and I'll show no abuse, just like regular use. But I hope that the no fun part will not be like true, because I think all of it is fun. Okay, so the first tool I'd like to show to you, those of you who are not already familiar with it, is Bloaty mcboatface. So it was developed by Google engineer Josh Haberman. It's open source, it's on GitHub. He wrote 2 great blog posts about the history and the motivation behind the tool. And the fundamental question it's trying to answer is, what is taking up space in your binary? And I think it can be enlightening. At the moment, it supports Linux and macOS binaries. And I think Windows support is kind of planned, but the author is looking for volunteers to implement that part. So here's just like a small dummy program that I'm going to use to demonstrate the features of Bloaty. I have 2 functions and like a global array and some stuff in there to take up the space. And let's suppose that I just compile it with debug info to a normal executable. And let's just first run Bloaty on the executable as it is. And we see a lot of stuff. In fact, we don't see everything because a lot of things are collapsed. So I'm going to expand that. Sorry, it's a bit too small, but like the details are not important at this point. So on the right-hand side, we see like the names of all the different parts of the binary. I'm going to return to that. And we see 2 columns of different sizes. So on the left-hand side, we have the file size, which is the number of bytes that that part of the binary occupies on the disk. And the other one is the VM size, which is the virtual memory size, meaning the number of bytes that that part of the binary will occupy in virtual memory once the executable is loaded. So to explore the difference between these 2 size types, let's first look at one part that says debug info. So you can see that this has 0 size in the virtual memory space, because when we start the executable, we won't load the debug information. So it only takes up space like on the disk. So we can say that this part of the binary only exists in the file size, on the file space. And on the other hand, for example, the BSS section, which contains the 0 initialized data from your program, has a 0 file size, because we don't have to store that on disk because we know it's just all zeros. So it's only going to materialize when you load your program. So we could say that it only exists in the virtual memory space. And to go deeper with all the different, what do the different parts of the binary like mean that we see on the right-hand side? We first need to talk about the file format for binaries on Linux. So it comes in 3 flavors. You can have a relocatable file, which is like during regular compilation, those are the O and obj files that you then link together. You can have an executable, which is already runnable, or you can have a shared object, which is kind of in between. And so the ELF file format needs to accommodate all like these three flavors of functionality. So I borrowed a picture from the book Linkers and Loaders, which kind of explains the structure of an ELF file. So when the linker looks at an ELF binary, it sees smaller sections. But when the system loader looks at the binary, it sees larger segments. Now, one segment consists of usually like many smaller sections. And the point is to take all the different parts of the binary that are going to be mapped onto the memory with the same level of access rights, bundle them together, and that's what is a segment. So to see how this works in practice, we can ask Bloaty to list all the segments in our binary. And so we are seeing these two segments, one with read and executable rights and the other with read and write rights. Now, I can list all the sections inside those segments. It's kind of small, so I'm going to zoom into the part where the two load segments are. And you can see that, for example, in the first segment, which has like read and executable rights, there's the .text section, which contains your actually the program code, and for example, the raw data section, which is the read-only data. And then for the other segment, which is the read-write segment, it has, for example, the BSS section that we saw earlier, and also the data section, which is like the writable data of your program. Another thing you can do with Bloaty is to track the effects of the changes you make to your source code on the binary. So I have my dummy program here, and as we saw earlier, my little global array is in the BSS section. Now, if I change it by initializing the first element of my array, I can watch it move from the BSS section to the data section, because it's no longer like 0 initialized. So I think that's cool. Bloaty also has a diff mode. When you have two versions of your binary, and you can see what's changed inside it. So let's suppose that I have an older version of my program on the left-hand side, which has just less stuff in it. And I can give my old binary after 2 dashes to Bloaty, and then it will generate a diff view. So for example, we can see that my doStuff function gained a lot in program code. And also, we can see that the 0 init symbol is completely new because I've just added it since like the last version of the binary. But the interesting part is, how does Bloaty know how to collect all this information from the binary? So let's suppose that I want to list all the symbols in my binary, and I also want to see for each symbol what sections it's referenced in. So this is also like very small, so I'm gonna zoom into our two functions, which is doStuff and main, and you can see that there's like a lot of sections in there. So my first thought would be to look at a symbol table, which like has an entry for my function and like a pointer to where the machine code starts. But that's just like a small part of everything that's connected to that function. So in fact, when you have a function, it generates a lot of other things into the binary. For example, unwind information for exception handling, relocation info, which it's not here, but it would be something like .relay.text, debug info, or actually the function's entry in the symbol table itself, because that's okay that like the symbol table entry like gets you the pointer to the machine code, but the symbol table itself is part of the binary and takes up space. So bloating goes a long way to find these all different pieces that are connected to the function to give you a faithful total size. But of course, in practice, it's not like perfect. So there will be some bytes in your binary that are unlabeled, and that's when you see the unmapped label. So that was the first tool. The second one I'd like to show to you is called Bolt. It was developed by Facebook engineers. It's also open source, it's on GitHub. And they also wrote a really interesting paper about it. What it does is binary layout optimization, meaning that it takes your binary and rewrites it in a way that it will be faster. So it currently only supports Linux binaries. And it takes like a tiny bit more time to set it up because it needs LLVM. So you have to check out the specific version, patch it, like clone Bolt, and then build it together. So what I have here shows how Bolt actually works. So we have two heat maps that represent the instruction address space of one of the Facebook services that is huge, and they are running it on their data centers. And so after running Bolt on this executable, what we see is that the hot parts of the binary, those instructions that were fetched from memory a lot of times, are more closely packed together, meaning that it's more likely that those instructions will fit into the instruction cache, and thus, like, the memory accesses will be, like, the binary will be faster. So this particular Facebook service became 8% faster on top of all the compiler optimizations and a link time function layout tool that they have. And another thing that the authors tried is running Bolt on Clang and GCC binaries. And what was really interesting that even on top of PGO and LTO, they managed to get the binary like a lot faster. And to like explain what I mean when I say PGO and LTO, I mean, of course, profile-guided optimizations, which are like a great feature in all of the major compilers. They usually start by building an instrumented version of your binary. Not always. I think Clang has support for sample-based profiling, but usually. And then you run your instrumented binary in a typical execution scenario to collect profile data. And then you use that data to rebuild your binaries. And all the optimizations in a compiler can use those PGO counts to personalize your binary and make it faster. So the great thing is that because you insert the profile information quite early in the compilation process, so many optimizations can benefit from them. But instrumentation, of course, has like CPU and memory overhead, which might make it not so practical when you have these large services like in a data center. And you can add LTO to PGO to make it even better. So link time optimization is basically when your compiler sees all the parts of your program as a whole and can do optimizations across like compile unit boundaries. So what can Bolt do like on top of all these great things? So one notable thing is that it can optimize third-party libraries when you don't have access to the source code, and also assembly code, which like compilers can't really do with PGO. It is supposedly designed to work with different compilers, where I think they mean Clang and GCC. And it uses sample-based profiling, which has like a very low overhead, and you don't have to like rebuild your compiler many times in special ways. And one more thing is that they apply the profile data collected on the executable on the binary level, which makes it more easier to use them, because when you use the profile information like on the IR, you have to project it back to the source, which can be difficult because from the IR to the binary, your code goes through like a lot of transformations that make them practically unrecognizable. So this step is easier. A quick overview of how the rewriting pipeline looks like. So they first look at a symbol table to find the functions that they want to optimize, read in the debug information, the profile data, and then use LLVM libraries to disassemble those functions, and then try to reconstruct the control flow graph to an extent that is necessary for them for the transformations. Then they run an optimization pipeline that I'll show in the next slide, and then they put your binary back together. So the optimization pipeline is a sequence of transformations very much like in a compiler, but like these operate on the binary. And I'm just going to highlight a few interesting ones. So for example, they run 2 passes of identical code folding, which your linker can also do for you if you specify the f function sections flag, which puts all your functions into their individual sections. But for a code that didn't have that flag, both can still find those duplicates and remove them. And it made like a 3% code size reduction for the Facebook service. There are some other transformations that use call frequency information to throw away calls or modify them in a way that makes them more performant. And these are really interesting. The reorder basic blocks transformations goal is to reduce the number of taken branches by rearranging the code in a way that hottest successors come after each other, so that you don't have to jump so much. And the reorder functions is that link time layout optimization tool that I mentioned at the heat map slide. And it uses like a reconstructed weighted call graph to do the function reordering inside the binary. So a typical workflow would look like the following. So first you have to have a binary that is large enough that it has instruction cache miss problems, because that's when it can really benefit from the tool. Then you build a copy of it while instructing the linker to leave the relocation information in the binary, because both will use it to do the function reordering inside the binary. And then you run perf on this modified binary to collect execution profiles, and then you feed the output of perf to LLVM bolt. And a few optional steps, like you can diff the running times of the 2 binaries and be happy that it got faster. And also, it also can be interesting to investigate like the reduction in instruction cache misses in the 2 binaries that you can do with perf. So to go like back a little to the Clang case that I mentioned earlier, so I said that Bolt was able to do the clang binary faster, even on top of the PGO-LTO build. And here I have a table of the reasons. So this is mainly like taken branches information of all kinds. And you can see that like all of these statistics were like reduced. Okay, that was actually all I had. So thanks for listening, and I hope you found something interesting. Okay, so I repeat the question. So the question was, do I have a sense of which parts of Bolt could be built into existing linkers? So Bolt already does a few transformations that are done by the linker, but for some reason, linkers sometimes don't have the necessary information to do them. I don't know. That's a really good question. I'm sorry. I would need to think about it.
Thanks for a nice talk. I was wondering, so you mentioned that you needed to pass additional flags to the linker to preserve more information, which I assume leads to a larger executable size, which is then optimized. Are those additional sections then stripped out when they're no longer needed by the Bolt thing? Or it's not possible? So I'm wondering, like, if I'm using Bolt, will my code size potentially be larger?
Necessarily, extra sections, it might be extra files for the linker.
Okay.
Give the answer for YouTube.
I'm sorry?
Give the answer for YouTube.
Oh, yeah, okay. So the answer.
Okay, I said that I'm guessing that some of these might be. Oh, sorry.
So basically the answer that I got was it's not necessarily additional sections directly in the executable. There might be additional files, so it's not necessarily leading to the growth of executable size. Okay, thanks.
Yeah, thanks. Yeah, thank you.